In this video, we're going to be going over Chapter 4, Reinforcement. For our definition to start everything off, reinforcement is the process in which a behavior is strengthened by the immediate consequence that reliably follows its occurrence. So we're talking about a process where a particular behavior becomes more likely to occur again in the future. So that's an increased probability of that behavior happening, is what we mean by saying it's been strengthened. And it's happening because of the immediate consequence, whatever happens immediately following doing that behavior. So there has to be some kind of reliable relationship between that behavior and the consequence that comes afterwards. So when we're looking at this, sort of breaking it down, we have that occurrence of a behavior. So the response that you're making, the behavior that you're doing, there's a consequence that immediately follows that occurrence of that behavior. So when a response is made, there is some immediate consequence, and the outcome of the interaction between that response and that consequence, the outcome is that the behavior is strengthened, or that behavior is more likely to occur again in the future. Now, in the past, you would have talked about this in terms of things like Thorndike's law of effect. So Thorndike was known, at least as much as we care about him here, he was known for his puzzle boxes. And those were where he was studying cat behavior. So cats would be placed into boxes where there was a particular sequence of actions that would allow them to escape the box. And so the behavior that we would be looking at is the cat's paw hitting a lever. And the consequence of hitting the right lever the right way is that the door would immediately open so that the cat could leave the box and food would be immediately available. So the outcome of this behavior of hitting the lever with your paw and then immediately getting out and having food available, so our outcome is that the cats are now more likely to hit that lever when they're in the box in the future. So that behavior has become strengthened because of the relationship between that consequence and the behavior. If we talk about, say, operant boxes, our second example from the first page, in an operant box, you have an animal that, say, presses a lever, and the consequence is that they get food. So in an operant box, you usually push a lever, or push a button, or peck a particular place on a touch screen. And so those behaviors have the immediate consequence of, in this case, receiving food. So that immediate consequence of getting food after pressing the lever leads us to the outcome that the animal is then more likely to press that lever in the future. So our occurrence of our behavior, the response that we're making, the immediate consequence that follows that response, and that gives us an outcome where the behavior is more likely to occur in the future. So that's reinforcement, and we're going to look at sort of the different pieces of this sort of relationship here throughout today's lecture. Now, when we talk about is the behavior strengthened, so the outcome here, strengthening of the behavior. So we're going to be also calling it sort of, is it more likely to occur again in the future? Has it been strengthened? Is there more of it? We can be talking about an increase in frequency. So if we're talking about pressing the lever, do they go from pressing it sort of once to pressing it 10 times? We can talk about an increase in duration. So instead of doing that particular behavior for 1 second, are they now doing it for 10 seconds or 10 minutes? Increase in intensity, are they pushing the lever harder or doing the thing with more intensity? We can also have an increase in speed, or we could call that a decrease in latency. So maybe instead of it taking 5 minutes for the cat to flip the switch that lets them out of the box. This time they're going to do it in a minute or maybe in 30 seconds. So all of these would be examples of strengthened behavior. So it doesn't necessarily have to be stronger in sort of a traditional sense of it. Any of these count as that behavior being more intense or more likely to occur again because we've changed some dimension of that behavior occurring. Now, our next definition is operant behavior. So if we're trying to define operant behavior, an operant behavior is a particular behavior that is going to be strengthened through the process of reinforcement. So we just did the definition of reinforcement, where that behavior is strengthened by the immediate consequence that follows that behavior having been done. So if we talk specifically about an operant behavior, it's a behavior that's being strengthened through this process. So when we talk about later on operant conditioning, that's going to be working on operant behavior. So an operant behavior ends up acting on the environment to produce a particular consequence. If that consequence, whatever stimulus or event that follows that behavior having been performed, ends up strengthening that operant behavior, ends up making it more likely to occur again in the future, we can call that consequence then a reinforcer. So if I hop to the next page here, we have the same setup here where we have an occurrence of a behavior, and we have this immediate consequence, which we're calling a reinforcer, because that immediate consequence is strengthening that behavior. It's making that behavior more likely to occur again in the future. So we've introduced this term here, reinforcer. And because this behavior is being strengthened in this particular relationship, we can call this an operant behavior. And when we talk about operant learning, that can be a change in a class of behaviors or a type of behavior as a function of the consequences that followed it. So operant learning is all about changing that behavior, adjusting that behavior based on the consequences that follow it. I will make a note that this isn't specifically tied to reinforcement. It doesn't have to be specifically for reinforcement. It will also work with punishment when we get to that later on. But it fits into the chapter talking about reinforcement, so it's coming up first here. All right, so this is our new arrow with our new relationship here, and nothing really has changed. We've just introduced a new term, and we have a little bit better of an understanding of what each of these components is talking about. So let's take a moment and see if we've got these terms down. So if I have a situation here, we say that Jim cries at night after being put to bed, and his parents come into his room to comfort him and calm him down. As a result, Jim now cries more often at bedtime. So if we're looking at this situation, what's the operant behavior? What's the behavior that's going on? And so if I hop back here, so it's going to be a behavior that ends up potentially being strengthened. So if Jim is crying, his parents come into the room and comfort him, and now he's crying more, then our operant behavior is going to be that crying. And then if we want to break it down into what's the reinforcer, what's the immediate consequence that is making it more likely for that behavior to happen, that reinforcer would be the parents coming into the room or the parents comforting him. So we can break this situation down and be able to talk about what's the operant behavior, what's our reinforcer, and we can kind of slot them into that sort of little model that we've put together. So a question like this is absolutely going to be showing up on the exam. You should get comfortable with these kinds of questions where you break down each of these situations into the components that we're learning about. Now, I already alluded to the fact that we will be talking about punishment a little bit later on, and that reinforcement and punishment work together somehow. From 104, you should remember having been exposed to both positive and negative reinforcement and punishment. In 104, we did a chapter on learning, and that was it. So we had to go over these things very, very briefly. So in a class all about behavior modification, we're going to get a little bit more time with these things, which is why we right now have an entire chapter just on reinforcement. So I'm going to refresh your memories about the difference between reinforcement and punishment, and then we'll talk about positive and negative, just to get us all on the same page as we move forward. So reinforcement, as we've already talked about, is a situation where we're increasing the likelihood of that behavior. We're strengthening that behavior. Punishment is basically the opposite, where it's some sort of event that because of the immediate consequence of making that response, of doing that behavior, our outcome from punishment is actually a decrease in behavior. So instead of strengthening a behavior, punishment decreases that behavior, decreases the likelihood of that behavior occurring in the future. So reinforcement is the behavior occurs more, it's more intense, it's more frequent, it's more something, and punishment is that behavior becomes less something. So less frequent, less likely to happen at all, takes longer for it to happen, something like that. Now for positive and negative, I always just use the idea of positive is that you're adding something and negative is that you're removing something. So for positive reinforcement, we can say that, so our occurrence of our behaviors, the response that we're making, has an immediate consequence that is some kind of appetitive stimulus. So we are adding something that produces the outcome of strengthening that behavior. So because you've gotten something good, you've gotten something appetitive, you are then more likely to do that behavior again in the future because you want to get this consequence more often. So an example of this is that a child gets dessert if they finish their dinner. So the immediate consequence of finishing your dinner is that you get dessert. You are given something, you are adding something that is good, and it makes you more likely to finish your dinner in the future. We can also have sort of, instead of a physical thing that you get, maybe you receive praise. So if a student answers a question well, then you're going to want to, if you get praise for answering a question well, then you're going to want to do that behavior of answering a question to get more praise in the future. So as an outcome, you're answering more questions. For negative reinforcement, negative means that you are removing something. So you are removing something, specifically something aversive, to make us more likely to do the behavior in the first place. So we have the occurrence of a behavior, the response that we're doing causes the removal of something bad. We lose an aversive stimulus, and that makes us more likely to do that behavior again in the future. So an example of this would be maybe your behavior is that you leave earlier in the morning, and as a result, you get to avoid traffic, which you usually get stuck in, and traffic is bad. Traffic is an aversive stimulus. So by leaving earlier, if you don't have to deal with traffic, if we remove or eliminate that bad situation, then you're going to be more likely to leave earlier in the future because you don't want to have to deal with that aversive stimulus. We can also talk about something a little bit more abstract, like sunglasses or even umbrellas could be considered negative reinforcers because for sunglasses, the consequence of putting on your sunglasses is that they take away the brightness or the excess light. Or using an umbrella is the consequence of keeping you dry or keeping the rain off. So they're preventing an aversive stimulus of too much light or getting wet, and the outcome is that you are more likely to wear sunglasses in the future, or you're more likely to use an umbrella in the future. For whatever reason, those kinds of examples tend not to occur to people as negative reinforcers, but they do absolutely fit the model here. Now, at the bottom, I have this reminder that negative reinforcement is not the same as punishment. So negative reinforcement, because of the negative side of things, negative means we're removing a particular stimulus. Reinforcement means that it's making that behavior more likely to occur in the future. So put it all together is you're removing something bad to make us more likely to do the behavior that removed the bad stimulus in the future. For punishment, punishment is actually when you're reducing the likelihood of something happening in the future. It doesn't have anything to do with sort of adding or subtracting. It's just a lot of people see that negative in front and assume punishment. So we're trying to rewire the way we think about this, because negative doesn't mean punishment here. Positive and negative just mean whether you're adding or removing a stimulus, and then reinforcement and punishment are telling us how it's changing our behavior, which direction it's moving in. Also, this is a good point to point out that reward isn't the same as a reinforcer. So a reward isn't always reinforcing, which I had to think about this one a little bit, because if we think of a reinforcer, it is a consequence that makes us more likely to perform that behavior in the future. It's like, well, that might be the same thing as a reward, because you think of a reward as being you did a good job, here's a thing. But the technicality is that they aren't sort of a complete overlap of ideas. A reward isn't identical to reinforcers. I think in my mind, the easiest way to think about this is that the term reward doesn't necessarily tell us that that thing that you're getting is reinforcing that behavior, that it isn't making a particular behavior more likely to occur. Reward is just that you are sort of maybe getting a thing. You are being rewarded for something, but it doesn't have that innate implication of how it's changing the relationship, how it's strengthening a particular behavior. So a treat might be a reward, but it's not necessarily reinforcing unless there's that underlying model that we've talked about here. So don't use the terms reward and reinforcer interchangeably, because they aren't necessarily conceptually equivalent. And for more like terminology to make sure that you're keeping things separate. So reinforcement is the procedure that we've been talking about. So where providing a consequence for a particular behavior ends up increasing or even maintaining the probability of that behavior occurring in the future. This maintaining, sort of maintaining the strength, is a new addition to our idea of reinforcement, but it kind of makes sense. So sometimes instead of, if a behavior when left on its own would sort of naturally deteriorate, would naturally lose strength, reinforcement that maintains that behavior, maintains the strength of that behavior, still counts as reinforcement, even if it isn't sort of on the surface making it much, much stronger. But so that's reinforcement is the specific procedure we've been talking about. A reinforcer is any event or stimulus that follows that operant response, that follows that operant behavior, and ends up increasing or maintaining its future probability. So the reinforcement is the process. The reinforcer is the event or stimulus, the thing that does the reinforcing in our model. So the terms aren't they mean something specific. And then we have our exact definitions of positive and negative reinforcement. So positive reinforcement is any event or stimulus that, when presented as a consequence of a behavior, increases or maintains the future probability of that behavior. Negative reinforcement is looking at events or stimuli that, when removed as a consequence of a behavior, increase or maintain the future probability of that behavior. Basically the exact wording of the stuff that we just covered with images. In 104, you would have also learned about some specific examples of negative reinforcement, and these are escape and avoidance behavior. So escape behavior is when that operant behavior increases because you've removed an ongoing event or stimulus. So there's some kind of aversive stimulus, say a really loud sound or a really unpleasant smell, and your behavior is going to make that stop. So press a lever to stop an electric shock, or if you leave your house to get away from the sound of a fire alarm. That would be an escape behavior because the aversive stimulus, the shock or the sound, was ongoing, and your behavior, your operant response, is to go elsewhere, to leave that situation, or to push a button that stops the occurrence of the thing. Your behavior allows that aversive stimulus to end. So you've escaped because you made it stop. Avoidance behavior is actually an interesting one, and this is when your operant behavior is increased. So you're more likely to do a behavior because it prevents the onset of that negative event or stimulus. So you press a lever to prevent a shock that would occur in the future. This one is a little bit more complicated because with escape behavior, you perform a particular behavior and it makes an ongoing bad thing stop. But here there's an extra step where you need to learn that a bad thing is going to happen and that there's a behavior that you can do to stop that thing that could happen in the future. So a really interesting example of this would be walking barefoot on asphalt in the summer. So in the summer, very dark ground gets hot. So if we look at that from an escape behavior idea, maybe you are walking outside on your driveway and you're in bare feet. You didn't realize the ground was that hot, but you're walking on it and it's really, really, really hot. So that aversive stimulus of your feet hurting because the ground is hot makes you want to get off the grass or get off the ground. So you head to the grass, and standing on the grass is much cooler. So in the future, maybe as soon as you start noticing that your feet are hot, you're going to be more quick to hop onto the grass because it'll stop the pain of having your feet be too hot. So you've exhibited escape behavior, and now you're more likely to do that escape behavior again in the future to avoid having your feet be too hot. For an avoidance example, if you know that the asphalt might be hot outside, maybe you're going to put shoes on before you leave the house. So your behavior is to put on your shoes. And when you go outside with your shoes on, your feet aren't hot. So you avoid the heat and pain from walking on hot asphalt. You've avoided that situation. And because you've avoided that aversive stimulus, you're now more likely to do that behavior again in the future. Now we just have a couple of things to keep in mind, a couple of little clarifications to make. Reinforcement itself is not a theory, so it's not the theory of reinforcement. We're talking about reinforcement as sort of a model to work within. Reinforcement is, instead of a theory, it is a functional description of the situation that's going on. So we've described a model. It's a functional description of a particular setup. Reinforcement is not circular. So there's sort of a specific way to actually talk about reinforcement. And this is this will be an interesting one because as time goes on and as you have more experience talking about these things, you kind of get used to the proper way to use them, but you might find that people who haven't specifically learned about reinforcement haven't necessarily got the fine details of how we're supposed to be using the terms. So we're going to be working on that throughout this class, and by the end of it, you're going to be pretty good at this. So an incorrect usage of reinforcement, or an incorrect usage of the ideas here would be to say something like the consequence, for example, food, increased the probability of response, example, lover pressing, because it was reinforcing. So we're not saying that the consequence did the thing because it was reinforcing. Instead, what we would want to say is that the consequence functioned as a reinforcer for the response, or the consequence reinforced the response. But we're always going to be implying sort of that relationship between the points here. So it's not sufficient to say that the response or the consequence was reinforcing. We want to say that it reinforced the response. For other terminology points, it's also correct to say that you are reinforcing a behavior or a response. So a teacher can reinforce standing in a line quietly using praise. So they can have that reinforcing of a particular behavior, standing quietly in line, and they're doing so by using praise. That's our reinforcer. But it's incorrect to say that you're reinforcing a person. So the teacher reinforced Sarah for standing in line quietly using praise isn't a correct usage because the reinforced part isn't directly working on the person. It's supposed to be working on the behavior. So over time, as we go through these examples, as we talk about these things, those distinctions will become a little bit clearer, and it'll get a lot more logical for you to talk about them this way. Now, the textbook talks about the exploratory power of reinforcement, and this is basically the idea that you have to figure some things out. That's the exploratory power, is that you have to look into things. So different stimuli will function as reinforcers under different conditions. So you kind of have to figure out that in a particular situation, which stimulus is acting as a reinforcer, or which stimuli are acting as reinforcers. Is there more than one? And which conditions are allowing that stimulus to have that function as a reinforcer. Different situations can have sort of the same stimuli act as different things. So sometimes it can be a reinforcer in that it will cause an increase in behavior because of its presence. Sometimes it'll cause that increase in behavior because of its absence. It all depends on how things are working together, how it's framed. So don't automatically assume that in every situation, food is always going to be a positive reinforcer or whatever, because there's always sort of a way of framing it, or a particular situation where it might be considered the opposite. So these situations are going to be fluid, and we're going to have to think through them as we approach them. And I've already kind of covered this point, the idea that an increase in the probability of is often shortened to simply strengthened, and I try and equate those terms by using them interchangeably as we talk about things. But yes, when we talk about a behavior being strengthened, we're talking about an increase in the probability of that behavior happening. Both terms are interchangeable. It's just a lot easier to say strengthened. So just know that that's what I mean. If I just say strengthened, it still means that we're increasing the probability of that behavior occurring. All right. So next we can talk about types of reinforcers, and we're going to get into sort of some of the details that make these models sort of more or less effective and variance upon the model, so lots of extra details to cover. So the first is that there are two main types of reinforcers that we're going to look at. An unconditional or a primary reinforcer is the first that we're going to talk about. And so this is specifically going to be a reinforcer that acquired its properties as a function of species evolutionary history. So you might think of these as reinforcers that have a particular property in some innate way. So as a result of evolutionary history means that it is sort of innate to the species that we're looking at. So these primary reinforcers are usually going to be stimuli and events that have some kind of phylogenetic importance, some kind of biological imperative. So things like food, sex, water, sleep, social interaction, and avoidance of harmful stimuli would all categorize as primary reinforcers because they are directly related to biological needs. When we use or see these kinds of reinforcers, it's going to usually depend on some amount of deprivation. Basically, food isn't always going to be a reinforcer unless the organism that you're looking at is actually hungry. So if you've just had Thanksgiving dinner and you have eaten your fill and you're so full you feel sick, if somebody offers you a turkey sandwich, that's not a great reinforcer because it has no appeal to you. So that only works if there's some amount of deprivation. Maybe you haven't eaten yet, then that food becomes reinforcing for whatever behavior we're going to look at. And different species have different stimuli that tend to work for them, whether it be types of food that they will or won't eat, or different kinds of social interaction that they enjoy, or whatever. There's lots of species-specific preferences here. So these are for primary reinforcers. And so we can actually have an example of an experiment that used a primary reinforcer. So in this case, our primary reinforcer is going to be social interaction. And so in this setup, we have Lieberman et al. Back in 1973. We're looking at patients who had schizophrenia. And they were going to, in this experiment, differentially reinforce incompatible sets of behavior. So basically they're saying that there are two behaviors that can occur, and you can only have one of them occur at a time, so they are incompatible. So if one is occurring, the other physically cannot occur, and vice versa. And by differentially reinforcing, we're meaning that they would reward or reinforce one of those behaviors and not the other. So here they're looking at rational talk and irrational talk exhibited by patients with schizophrenia. So rational talk meaning sort of clear, coherent speech that made sense, and irrational talk would be sort of incoherent, nonsensical speech. So clearly those behaviors are incompatible. You can't have both happen at the same time. So they were reinforcing the rational talk with social interaction and attention, while not providing those things during irrational talk. So this attention came from sort of one-on-one attention with either the doctors or the nurses. And so that behavior that, I guess that would be the consequence in this situation of rationally talking, that's our behavior, is that they would get more interaction, more social interaction, and that should theoretically cause an increase in rational talk, a strengthening of our behavior of interest because of that particular consequence. And we can say also that they didn't reinforce the irrational talk. So that's why it's differentially reinforced. And we can look at over here where we have a multiple baseline across subjects setup where we have 4 different patients, and their treatments started at different times so that we can look at sort of the before treatment and after treatment. So before treatment was how much rational talk were they exhibiting to begin with, and this scale is minutes of rational talk per day. And so they were tracking it here, and lower minutes of rational talk means that they would be doing the opposite, which is irrational talk more often. And then at the treatment, we see a rise here where they're starting to show more minutes of rational talk once that reinforcement was added. And each individual showed an increase after that treatment point. And so we do see that each individual had their own baseline to begin with, but our scores after the first treatment, or after this sort of treatment onset, are all higher than their baselines, even if they're different from each other. So a practical illustration of a bunch of terms we've talked about so far. Now, that was our primary reinforcers. Our second type of reinforcer is a conditional or secondary reinforcer. Now, a secondary reinforcer is an otherwise neutral stimulus or event that has acquired the ability to reinforce something due to a contingent relationship with other typically unconditional reinforcers. So basically we're saying that this is a stimulus that on its own was once neutral, but has now become a reinforcer because it was paired with something else, because it was paired or associated with a primary reinforcer or something that had already been established as a secondary reinforcer. So a fantastic example of this is money. So money on its own doesn't have any intrinsic association with anything. It isn't on its own reinforcing because it's just pieces of paper. So if we removed sort of the meaning behind it, if you couldn't use money to buy things, it doesn't really have any value to us. It isn't reinforcing, but because it has that association with, it can get you things. You can use money to buy food. You can use money to pay for events. So money becomes a conditional or secondary reinforcer because it gets you either other secondary reinforcers or other primary reinforcers. So the stimulus on its own would have been neutral, but it's become associated with other things, so now it itself is a reinforcer. Now for the next couple of slides, we're going to talk about factors that influence the effectiveness of reinforcement. So our variables that can affect reinforcement, and there are tons of factors that can take effect here, so we're going to kind of work through a bunch of them. So the first is the idea of immediacy. And so we can say that a stimulus is more effective as a reinforcer when it is delivered immediately following the behavior. So if our consequence happens immediately, it's going to be a lot more reinforcing because it happened right away. So we can say here that this is probably something to do with making it a lot easier to form an association between the behavior and the consequence. If they occur close together in time, then it's a lot easier to link them together and know that one is a consequence of the other. You can also have an immediate sort of time link. There's also sort of the spatial link, where if it's happening in the same space or close together physically, then it's easier to link. Those are kind of closely related here. Another factor that's really important is the specific reinforcer that's being used. So individuals have different preferences. So if we're trying to find something that is reinforcing for an individual, what's reinforcing for one person might not be reinforcing for another person. So if you prefer chocolate over sunflower seeds, then maybe you'd want to use chocolate as a reinforcer. But if somebody prefers sunflower seeds over chocolate, then maybe for them you want to use sunflower seeds. In a lot of the literature, you might see a task where they actually determine an individual's preference in the initial setup of the experiment so that they know that the reinforcer being used is actually a reinforcer. So they'll have a couple of different candy options, and they'll see what the participant prefers because the specific type of reinforcer being used actually affects the effectiveness of the whole process. Another thing to keep in mind are the characteristics of the task itself. And this is a really, really cool one. So if the behavior, if the task that you're having the organism do sort of naturally associates with that particular consequence, then it's going to be a lot easier for that reinforcement process to happen. So a pigeon pecking for food is a natural association because when pigeons are looking for food, they peck at the ground. So if a pigeon is going to peck a key and their consequence is to get food, that's a pretty easy association to make. So that's a good idea. That's a good characteristic for that task because they match. So they are sort of congruent with one another. But if you have a hawk, and the hawk has to do a pecking behavior for food, that's actually a little bit harder. And that's because when hawks are getting food, they don't peck at the ground. They would do grasping with their talons. They would do sort of pulling at things with their beaks, but they don't peck. So having that requirement of pecking specifically for a task that would give them food, there's a little bit of a disconnect there. And so it wouldn't be as effective in our model. So you'd want to find a different task for the hawk that is more in line with behaviors that match with food getting behaviors. Another thing that we want to keep in mind is contingency. And this is the definition is that a stimulus is more effective as a reinforcer when it is delivered contingent on the behavior. And this is a fancy way of saying that our stimulus is going to be a lot easier to link with that behavior if it is exclusive to that behavior. So if you have a pigeon in a box and they're pecking a button to get food, they're going to more readily form some kind of association with that button and food if they only get food when they push the button, and if every time they push the button, they get food. So you can have sort of that strong interrelatedness where food's associated with the button, buttons associated with food, and not linked with anything else. The stronger that relationship, the more exclusive that relationship, the better your setup is going to be and the more learning we're going to see. And so this contingency isn't just about sort of the exclusivity of the thing. We can also have it related to sort of the nearness of events in time, kind of relating to sort of immediacy. So if we know that there is temporal contiguity where you push the button and food immediately appears, we have that spatial contiguity, which I already kind of talked about earlier on. I always get ahead of myself, where you push the button and food is dispensed in that same area. Having high contiguity in those cases could give us this idea of pairing, so we can call it pairing. And I'll use those terms fairly often. So I'll say that pushing the button is paired with an immediate display of food or something like that. So some of the terminology will come up more and more often. So less contiguity, meaning sort of longer delays or a larger physical distance between where you push the button and where you get the food, can diminish the effectiveness of that as a reinforcer. And this degree of contiguity, so more or less contiguity, would be described by the hyperbolic delay function, which is actually on the next slide. And so I guess before I move on to that, I just want to say that this contiguity, pardon me. So I want to take a second actually here to specify the difference between contingency and contiguity, where contiguity is kind of like another way to explain immediacy, but it's basically saying that there's a close pairing of the two concepts in either time or space or whatever. And contingency is sort of the umbrella term under which we're talking about contiguity. So as we said, our contingency is focusing on that link where a particular stimulus is completely contingent on a behavior, where you only get a particular consequence when you do that behavior, and that stimulus only happens after that behavior. That's that contingency side of things. And when we talk about sort of the quality of that contingency, that quality of the things that we're relating, that's when we're talking about contiguity. It had just occurred to me that having two terms that both start with similar roots, it might be kind of easy to think that they're interchangeable, but the contingency is talking about sort of how exclusive the consequences to the behavior and how that consequence follows that behavior. And then the contiguity side of things is talking about sort of how closely associated are they, how quickly do they happen together, that sort of thing. So this is the general relationship, and this is kind of talking about the nearness of that relationship. So hopefully that helps just a little bit before I move on to talk about this hyperbolic decay function. Yeah. All right. So hyperbolic decay function. This is basically saying that usually you do the behavior and then there's a particular consequence. Then, so you do the behavior and then you get food. That reinforcer will happen. And so we have a function here. This is the equation for it that shows a particular value that we put on that reinforcer. How much do we want that food? How much is that food worth to us? And at the bottom we have a delay. I believe this is in seconds, but like the units don't really matter here. And so the idea is that if you get that reinforcer immediately, if you get food immediately, then it has a lot of value. You really, really want it. It has lots of value. The value has not decayed. But as there is a delay, as you have to wait to get that reinforcer becomes less valuable. And so over time, we see this drop off in how much that particular reinforcer is worth. And so each of these lines would say describe a different kind of reinforcer. And so this equation is here just to talk about sort of what's going on. So our A is our max reinforcing value. So where do we start at if you get it immediately? K is a rate for discounting. This is basically going to be specific to the particular kind of reinforcer that you're working on. Some reinforcers have a very rapid decay rate. Some have a little bit of a slower decay rate. So that K will change depending on what kind of reinforcer you're looking at. D is the delay, so where on this diagram are we falling? And then V is then our total value for the reinforcer. So D is where we're scoring on this axis, and V is then where we score on this axis given whatever period of delay we're on. So we would calculate V to determine where we're sitting at any particular time. So for this case, I'm not going to have you do a calculation like this on, say, an exam. Maybe you would see it on an assignment. But the important part here is to note that this K value changes based on an individual reinforcer, and sort of the D and V are giving us our two axes. And then we have our start point. So things to keep in mind. All right, so continuing on with this idea of contingency, so that's that degree of relatedness or correlation between the behavior and its consequence. If we want to see how important this is, how important it is that pushing the button gets you food and you only get food when you push the button, we can actually look at a diagram down here, which is going to be showing the rate of responding over a particular number of trials, and we have different setups here. So we have sort of a moderate contingency where there is an association between pushing that button and getting that food, or zero contingency where sometimes you get food and sometimes you don't, and sometimes it follows pushing the button and sometimes it doesn't. And we can actually see that there's a lot more responding when there's some kind of contingency or association or correlation between a particular behavior and the consequence, and there is very little of that behavior when that contingency goes away. And this is sort of reversible. As soon as the animal learns that there's no correlation between pressing that button and getting food, they're going to stop pushing the button, because why would they push it if they're not getting something out of it? But if there is some kind of correlation between the two, then they're more likely to do the behavior because they're getting the food. So we're seeing that contingency, we're seeing that relationship, and it's changing the behavior. Now, for a real life example of contingency, a really good one here is using a key to start your car. So turning your key in the ignition is a reliable way to start most vehicles. As long as your car is in working order, turning the key in the ignition turns the car on. And the car doesn't turn on without the key being turned in the ignition. So there's a really strong contingency there where if you want to turn your car on, you have to put the key in the ignition and turn it. So there's a strong contingency there because there's such a good association, there's such a strong correlation there between that behavior and the consequence. I have noticed that I have a couple of duplications here with specific reinforcers and task characteristics. I moved some stuff around and apparently forgot that I had already covered these, so we can skip that slide because we already did that. More things about characteristics specific to our reinforcer. We can talk about what are called motivating operations. These are sort of like extra characteristics that we need to keep in mind. So one type of motivating operation is an establishing operation. And an establishing operation makes a stimulus more effective at reinforcing, as a reinforcer at a particular time. So we've already kind of talked about the idea of deprivation. So food isn't necessarily a great reinforcer if you have recently eaten. So an establishing operation would be maybe you do something that makes food more appealing. So depriving pigeons of access to food for a little while before a task helps ensure completion of a task that uses food as a reinforcer. Other examples, so practical examples would be something like free salty popcorn. That could be an establishing operation because once you start eating it, then you have that sort of salty feeling in your mouth. Now you're going to want to drink. Maybe you're going to want to keep eating. So you have made continuing to eat, or if we wanted to look at specifically drinking, you've made that more appealing. So it serves as an establishing operation. Another thing we can look at are abolishing operations. And these are kind of the opposite. So these would make a stimulus less potent as a reinforcer at a particular time. So the opposite of deprivation would be something like satiation. So if we're looking at food examples, if you have just eaten a large meal, food is now no longer a good reinforcer because you're now satiated. You have eaten recently, so food is not a good reinforcer anymore. Another example would be if you ask somebody what their favorite song is and they tell you, and then you play that song on loop for the entire session. So it might have been a decent reinforcer at the beginning, but because they've heard that song over and over again now, it isn't as good as a reinforcer because they've already heard it recently. So we have these two kinds of operations that can kind of modulate the effectiveness of a particular reinforcer at a particular time. Our next reinforcer characteristic to consider is the magnitude of our reinforcer. And in general, a more intense stimulus is usually going to be a more effective reinforcer. Usually. This isn't always the case. So if we think of our standard case, more intense means a more effective reinforcer. However, the relation between the sort of size or magnitude and the effectiveness of that stimulus isn't linear. It isn't sort of a 1-to-1 ratio. So in general, the more you increase that magnitude, the less benefit you get from that increase. So we're still going to see sort of an increase, sort of a positive correlation here, but it isn't going to be a linear correlation. It's going to sort of flatten out as you go. And the effectiveness of especially unconditional reinforcers tends to diminish rather quickly. So an example of this for magnitude being important would be that you would work a lot harder to get out of a burning building than you would to avoid being out in the sun that's just a little bit too hot. Sort of one is way more intense and is going to cause a lot more intense of a behavioral response than the other, just by nature of magnitude. But if we want to look at this relationship between the magnitude of the reinforcer and the intensity of the behavior it exhibits, we can look at two graphs here. I want to stress that this graph is what we would expect to see, but it isn't actually what we observe. So this is what we would see if there was a 1-to-1 ratio between the increase in behavior and the increase in the reinforcer. So this is what we would anticipate if there was a linear relationship where increasing here the magnitude of our reinforcer by 3 causes an increase in the amount of behavior by 3. So if you're doing a particular behavior to turn down the volume on your TV, if the volume increases by 3, you're going to directly do something 3 times to make the volume go down or something like that. So this is what we expect, but it isn't actually what we observe. What we see is a lot more of a curve here, a non-linear relationship, not exactly logarithmic, but that's what it makes me think of. So this is what we actually see, where at first we see a pretty decent relationship between the change in magnitude of the reinforcer and the amount of behavior that we see. So at the beginning, a small change in reinforcement magnitude gives us a pretty big change in behavior. So here we're seeing a change of like 0.8 versus the 1s that we're seeing here. But as time goes on, the amount of change that we see here is much smaller. So to see that same sort of height change here, to see the same change in behavior, we would have to have a much, much larger change in reinforcer magnitude. So as we get a larger magnitude of the reinforcer, we see less and less change in the amount of behavior. So an example of this would be maybe we've set up an experiment and we've specifically set it up so that you're thirsty now. We've deprived you of water for half an hour, and we gave you salty popcorn to make sure that you were going to be thirsty. And our reward is that you can have a small glass of water, just one mouthful. So that might get you to do the behavior of interest. But maybe if our reward or our reinforcer, if our reinforcer was a larger glass of water, maybe I would give you a whole bottle of water. You'd be a lot more motivated then to perform that behavior. Okay, so what if we keep going up? So if a mouthful of water was enough to get you started, a whole glass of water seemed a lot more appealing. Well, what if I give you a whole water cooler full of water? It's like, well, that's still going to be more reinforcing, like it's still going to get more behavior, but there's kind of a point where that's more water than I know what to do with. So one water cooler worth of water versus 2 water coolers isn't necessarily going to change my behavior all that much, because at such a large magnitude of our reinforcer, it doesn't really matter as much anymore. So at the beginning, small changes can cause pretty large changes in behavior, but after a time, even large changes in the magnitude of the reinforcer doesn't necessarily have a huge change in the amount of behavior that we see. So that's what we see. This is what we would logically have anticipated theoretically, but isn't what we see. This is more close to the truth. All right. And sort of one last reinforcer characteristic to consider is the fact that there might be competing contingencies. Now, this kind of relates to the final section in the chapter in the textbook that talks about concurrent schedules of reinforcement, where you have sort of multiple things going on at once. But when we're talking about competing contingencies, you have to sort of choose which behavior you're going to engage in. So maybe you have to decide, should I watch YouTube or should I study? In the case of this class, you're kind of doing both, where watching this on YouTube means that you are studying. But if you had to choose between, say, the automatically coming up next is a video from one of your favorite content creators, and you're thinking, well, I should be studying, I should be taking notes and reading the textbook to go along with this lecture, but I really want to watch that video, which one do you pick? So how do you choose between competing contingencies? And we tend to see that people will engage in behavior that gives them either more frequent reinforcement, or a greater magnitude of reinforcement, or quicker reinforcement, or that they're going to get reinforced with less response effort. So basically, people want to get more out of it for less effort in some way, shape, or form. So we kind of have to keep in mind not just the one particular contingency that we're looking at, but what else is also going on. Now, this idea of different contingencies sort of co-occurring brings us to the next topic, which is the Premack principle. And so a little bit of background here. As you know, in nature, different types of behaviors have different probabilities of occurring. So different things are going to happen at different rates. Different things are more likely to happen than others. So eating is going to be probably a high probability because things have to eat all the time. So a food-deprived rat is absolutely going to want to try and find a way to eat. Lever pressing is a kind of behavior that's probably low probability. These types of instrumental responses tend not to occur naturally. So this would be a lower probability event because it's less likely to happen on its own. Our Premack principle states that if we have these lower probability events happening first, and doing this low probability event gives you the opportunity of performing a high probability event, then we will see reinforcement for that low probability event. We have that illustrated down here. So our low probability of event happens first and gives us the chance to do the high probability event. Then it's going to reinforce that low probability event. So pressing a lever is low, but if pressing a lever gives us the chance to eat, and eating is high probability, then getting that chance to eat is going to reinforce that lever pressing behavior. Interestingly here, the converse isn't true. If you get to do the high probability thing first and are then given the chance to do that low probability thing, we don't actually see the same kind of reinforcement there. Because if you're given the opportunity to eat and then given the opportunity to press a lever, why would you bother pressing the lever? Because you already did the high probability thing that you actually wanted to do. So we don't see reinforcement for that high probability thing. So if we want to say that in sort of plain English, we would say that high probability behavior can reinforce low probability behavior. So it's kind of like that high probability behavior sort of slots into our reinforcer point on our model, and it makes it more likely for us to do the low probability behavior. Now, we see this quite a bit in practice, especially with children. So if a child prefers playing pinball to eating candy, you can reinforce candy eating by letting them play pinball each time they eat some candy. It's kind of a weird example because we could frame it the other way around, where if they prefer eating candy to pinball, you could reinforce pinball playing by letting them eat candy. You also see this with, say, getting your kid to eat their vegetables. So it's, if you eat your vegetables, then you can have dessert. So that high probability behavior, being able to have dessert, ends up reinforcing our lower probability behavior, eating your vegetables. Now, you can probably see a couple of problems with this. This doesn't nicely account for conditional reinforcement effects. Conditional reinforcement looks specifically at if you do this particular behavior, it makes it more likely for a particular outcome to occur, for a particular consequence to happen, but it doesn't guarantee that it will happen. So it doesn't, or this Premack principle doesn't quite fit with all types of reinforcement and all sort of aspects of it, so it's not great on that count. And we have this weird situation where low probability behavior can actually end up reinforcing high probability behavior, specifically when the organism has been deprived of the low probability behavior. So for example, rats really like running. That's a high probability behavior for them. So they like to run, they want to run, and they will drink water to be able to get access to a running wheel. So they will then, that would tell us that drinking water is a low probability event in comparison to running in this situation. But if the rats aren't given access to water, they will run to get access to water. So by adding in this idea of deprivation, we can actually kind of reverse the contingency so that the formerly framed as high probability behavior so the formerly low probability behavior ends up reinforcing what was framed as the high probability behavior instead of the other way around. So effectively, deprivation can cause a reversal of our Premack principle. So it's an interesting way to look at things, but it doesn't directly seem to explain everything. So that's why we only talk about it very briefly here. There are some applications for this principle. So if you look at clinical patients, if you find out what behaviors they find reinforcing, what are their high probability behaviors, you might be able to reinforce particular low probability behaviors. So if patients really don't like sitting still, maybe you can give them the chance to do something that they really enjoy, maybe give them social interaction if they do the thing that is a lower probability, like sitting still. And so this in clinical settings is a great way to change some of the behaviors to sort of reinforce particular behaviors by giving them the opportunity to do something that has a higher probability. Now, this is a good spot to point out again that reinforcers are sort of responses, the specific behaviors, and they aren't like you're sort of reinforcing a behavior and you're not trying to change a particular diagnosis, I guess. So you're not reinforcing or changing schizophrenia itself. You're reinforcing a particular behavior in patients who have schizophrenia. I just find that there's some weird wording that goes on in some of the literature. So you would be reinforcing the behavior of sitting still, specifically in individuals that have schizophrenia, as opposed to having that reinforcing acting directly on the disorder itself. Okay, for the last section of this lecture, we're going to talk about schedules of reinforcement. And again, you've done schedules of reinforcement before, but we're going to go through in a little bit more detail than what you would have seen in 104. So a schedule of reinforcement is basically a rule describing the delivery of reinforcement. So we have different schedules that end up producing unique schedule effects. And our schedule effects are particular patterns or rates of behavior that occur over time. So we'll see different graphs showing the outcomes of different schedules of reinforcement. They each have different effects. Over long periods of time, the effects of these different schedules of reinforcement are very predictable. We can look at a particular graph and be fairly confident in concluding what kind of schedule of reinforcement we're seeing. And these types of schedules of reinforcement and the resultant schedule effects occur in lots and lots of different species, including humans. So this topic is going to apply to lots and lots of things. So we're going to break down all the different kinds of schedules of reinforcement, but before we do that, I want to talk a little bit about how we look at schedules of reinforcement, because we're going to be seeing a lot of graphs and a lot of sort of setups, and I kind of want to explain where they're coming from. So most schedules of reinforcement research, anything including schedules of reinforcement, is going to include a cumulative record. This is based on this old cumulative recorder device. So this is back in the 50s. You can see different variants of this earlier or later, but basically before computers, there would be some kind of measurement of how many times a particular behavior had happened. So I like thinking about this, say, as monitoring an operant box. So you have an operant box, there's a rat inside who pushes a button for food. So over time, we will see jumps each time that button is pressed. Now, what's happening with this device is that we have a roll of paper on the device, and the paper is going to unroll at a consistent rate. So as time goes on, it's going to unroll maybe a centimeter a minute. And so if we know exactly when the experiment starts, when did we hit the switch, when did we turn on the device, that would be, say, point A, we know how long it's been from the start of the experiment until a particular behavior happens. So at the beginning here, we see a flat line, and this line would be drawn on the paper with, say, a pen. And so this pen is going to hold steady until something in the box triggers the pen to move. So we get that flat line with no responding because nothing has happened. And then when we see this little jump upward, that's when the first response has occurred. So the rat presses the button and it causes the pen to hop up to the first level, indicating one response has been made. And then there's a little bit of a flat line after that because nothing happens until the next response is made. And so these little staircase marks here are showing us that the rat is pressing that button every whatever unit time is covered here. So if this is 1 centimeter, and we said that the paper is unrolling at 1 centimeter a minute, then we would say that there's a minute between each of the button presses. As we get up further, we can see that these little steps actually end up getting smaller. So if this length has gotten shorter, maybe they're pressing the button every 30 seconds instead. And maybe we're seeing here that the vertical height is lower. So maybe there's a difference between pushing the button halfway and pushing it all the way in. So you can set it up to have different actions happen with the pen on the paper based on whatever's happening in the box. So over time, as more responses happen, the pen moves farther and farther over. So we get a cumulative record where we accumulate the number of presses that have happened over time. And so it sort of stacks as we go. And so here we can see maybe they reset it, maybe they started over, maybe we hit the maximum for this particular sensor and it's just been told to roll over. However this was set up, that's sort of how they would read it. This tradition, this sort of method of showing the data has persisted because this is what people got used to looking at. So now even though we have computers and we can have sort of an accurate printout of which response happens at which point in time, it's still pretty easy to look at a graph like this and see, okay, here's when they're responding, here's how close together the responses are, here's where they pause, that sort of thing. So this is where it's coming from, and it hasn't really changed that much right now. So modern graphs are going to be looking basically the same. So this is a cleaned up version of what we just saw here. And that point where we sort of hit the top and it came back down again in the physical machine, yes, that is when a pen resets. We won't see much of that if we're looking at data that's happened since probably the 80s onward, unless they're using really old equipment. But we have sort of our response is where that jump up happens. We can have flat lines being periods of no responding. And so differences in this length here are showing us sort of how close together the particular responses are. So if we labeled this graph based on this kind of an output, we'd say these are our cumulative responses, and this is our time in seconds. Now, we can get more information from this, where if we have sort of more time in between responses, we can get a rough slope of this line here and say there's a low rate of responding. There's very few responses accumulating over this long period of time. So there's a low rate of responding. And then up here, where we're seeing more of a climb and less time between each of those responses, we'd say that's a high rate of responding. So this is a sort of non-steep slope, and this is a very steep slope, so that tells us that there's a difference in the rate of responding. I also want to point out that sometimes you'll see very similar graphs, but set up just a bit differently, and this is when you don't see those steps. So this is still cumulative responses, but without using these steps. So this is just sort of an alternate way of presenting the same data. So flat lines instead of steps, but you'll notice that, wrong way, the peaks here, the like sort of points of the steps correlate to different data points. So it's the exact same information, just presented in a slightly different way. So sometimes you'll see this from a paper and it means the exact same thing. Now, I guess it's also a good time to point out the difference between frequency of a particular behavior and cumulative frequency of a particular behavior. So most of what we see in behavioral data is that cumulative frequency, like we just talked about here with our cumulative record. So over time, we see this gradual climb in the line. So each time a new behavior is made, it's added to the record. We might be more used to seeing things like sort of absolute frequency, which is at a particular unit of time, how many responses are being made in this particular window. So if we have the same data here, so this is showing us the exact same data. At time 1, nothing, time 2, nothing, which we see here, 1 and 2 are flat, no responding. Time 3, we see our first response. So at 3, we have a frequency of 1. So that's the first jump up. Then we start seeing things change because at time 4, there's one more button press, there's one more action. So the frequency stays at 1 if we look at just frequency. But if we're looking at cumulative frequency, that is our second response in the overall experiment that we're looking at. So the frequency here is only looking at time period 4, or in that particular window, there was one behavior. And our cumulative frequency is saying that that new behavior that occurred is the second that has occurred overall, so now we're reading 2. And so when we move down to time 5, there are 2 responses that happened in time period 5, and that gives us 4 cumulative responses. So the cumulative frequency looks very different from our absolute frequency, but it's just because it's telling us something a little bit different, but it's the same basic information. It's all about how it's presented. And again, you can see it as a step function or as, or as these sort of data points. It's, again, kind of whatever the author of a particular study decides to use. These graphs are identical to these graphs in terms of information being presented. They're just using slightly different methods. So we'll see a lot more of these kinds of graphs, but they're not the only thing you see, which is why I tell you about these guys as well. So just to be braced for what you're going to see. All right, and we can also look at slopes. And again, if we have this difference between frequency and cumulative frequency, obviously our slopes are going to be different because the data is being treated in a different way. So if our slope is specifying the rate of change in y, our behavior, for every unit time, our x-axis here, it's telling us how much of an increase over time is happening, or decrease, I suppose. It's just the rate of change. So a larger slope means higher rate of responding over time, but you have to consider if you're looking at frequency or cumulative frequency, because this is telling us that yes, they're responding more overall per time period over time. So there is a positive slope here, but we have a much larger slope or a much more positive slope here with our cumulative frequency, because even if they were responding once per minute for the entire, say, 11-minute period, we would still have a slope that is at 1. But if we had one response per minute over 11 minutes and are only looking at frequency, we would have a flat line. So slope can be useful, but you absolutely have to keep in mind what we're looking at, because that changes how we interpret the data. And here our R² is being reported as a measure of how well our model is fitting the data. So how good of a line is this regarding the data that we have here? Okay, so with all of that background out of the way, we can get into the actual schedules of reinforcement. And this is going to be a little bit more straightforward. So for our schedules of reinforcement, we have 2 basic broad categories. We have continuous reinforcement schedules and intermittent reinforcement schedules. Continuous reinforcement schedules occur when the behavior is reinforced every single time it occurs. So a rat in an operant box pushing a button for food, every time they push the button, they get food. That is a continuous reinforcement schedule because every button press, every single one gets food. So these are great because the rate of behavior increases rapidly, because we have this very strong association between pushing the button and getting food. They learn to push the button very quickly because it is always associated with food. We have that really strong contingency here. So this is very, very useful when you're shaping a new behavior. So if you're trying to teach a rat to push a button, this is the best way to start off, because they're going to learn very quickly that the button gets them food. Unfortunately, this is very, very rare in the natural environment. It doesn't always work out in the natural environment. So this isn't always the most naturalistic way of going. Our intermittent schedules of reinforcement might be a little bit closer to what we see in nature, though each of the different types that we're going to talk about have sort of different pros and cons and different relations to things that we see in nature. So we'll discuss each of those. There are many different types of schedules of reinforcement, but we're going to focus on the 4 main types. As you start looking at scientific literature, you might see variations on these, but this is going to be a good sort of establishing ourselves and getting the ground rules for intermediate schedules of reinforcement. And you'll notice that intermediate schedules of reinforcement overall, we don't really have its own code to talk about, because if we're talking about an intermediate schedule, intermittent, not reading words great today, guys. Intermittent reinforcement schedules, we're going to talk about the specific kind of schedule most of the time, whereas a continuous reinforcement schedule gets its own abbreviation here of CRF, because if we talk about it, it's telling us exactly what's going on, which is sort of 1 response equals 1 reward as kind of an outcome. We have sort of a shortened form for each of the main types we're going to talk about for these intermittent reinforcement schedules, because when we talk about these, we're more going to care about what's going on in each of these specific types. All right. So I always like looking at the sort of, what are the words here and what do they mean? And we have 2 dichotomies. We have fixed versus variable and ratio versus interval. And at the front, before I get into them sort of broken down, I like to talk about sort of each of those dichotomies. So fixed versus variable. Fixed meaning sort of an absolute number of things or an absolute timing. Variable meaning that we're looking at an average with a little bit of wiggle room on either side. For ratios versus intervals, ratio is looking at, say, absolute number of button presses, whereas an interval would be looking at how much time passes. So I like to look at sort of those 2 options separately before going into each of the 4 combinations of those, just because it helps my brain sort of understand what's going on a little bit better. But that will make more sense as we break them down into each of the 4 types. So if we have a fixed ratio schedule or FR schedule, fixed meaning that it's going to be some kind of absolute, and a ratio meaning that we're looking at a number of responses. So our behavior is reinforced after a fixed or set number of times. So with our button pressing example, every X number of button presses, you get some kind of food reward. And these will be noted as FR and then the number of responses that are required to get reinforcement. So with our button pressing example, an FR of 120 is telling us that you have to push the button 120 times before you get food. Now, this kind of a setup generates what's called a post-reinforcement pause, or PRP. And this pause is going to typically increase with however large this number is, and with reinforcer magnitude. So what we're seeing over here is, so this is again that kind of graph that we just talked about, where we have sort of gaps where nothing is going on, then there's going to be a bunch of reinforcing. Each tick on this graph, or each sort of step on the stair there, is showing that a reward was given. That little tick is indicating that the animal got their reinforcer at that point. Maybe they got food. And after that, we see this plateau, and that is our PRP, or post-reinforcement pause. So you can think of it as the rat just pushed the button 120 times and got food pellets. And because they just got food pellets, they know that the next time they push the lever there, or push the button, they are absolutely not getting food, because now they need to push the button 120 more times before they get more food. So the more times they have to do that behavior, the longer they're going to wait until they start up again. Also, the size of our reinforcer or the magnitude of our reinforcer can affect this. If they got a lot of food, they're not going to want to start pushing that button again for a little while. They might be satiated. They might be content with the food that they have before they're willing to put in that effort again. And once they then decide to start pushing the button again, once those responses start, so once our post-reinforcement pause ends, we see a slope here. And that slope is showing us our run rate, which is basically how much are they pushing that button in that time period once they start pushing it again. And so here we tend to see very sort of consistent slopes where once they start pushing the button again, they're going to do so at a fairly consistent rate. So we generate a steady run rate following that post-reinforcement pause. So there tends to be a pretty linear slope once they start pushing the button again. And we can have sort of different slopes here showing different rates of responding. So lots of information from that diagram there. Actually, before I move on, I should, I guess, give an example of this in the real world. If you are a newspaper deliverer and you get paid for every 50 newspapers you hand out. So you're going to hand out 50 newspapers, and after the 50th one, you get paid. You're not going to want to start handing out newspapers right away again. You just got paid, maybe, and the next paper you deliver, you're not going to get paid. So maybe you're going to wait a while, but eventually you'll be like, yeah, I need to get paid again. I'll go deliver newspapers. So you're going to deliver them at a pretty set rate. All right, variable ratio schedules. Because we're still looking at ratios, we're still looking at the number of responses required, but because now it's variable instead of fixed, now we're looking at an average number of responses. So in this case, we're saying that the number of responses needed to get reinforcement is going to vary each time. But our ratio requirement is going to vary around some particular average. So here we can have a VR of 360. So this is saying that you need approximately 360 responses in order to get reinforcement. Now, what you might see is anywhere between here in this data set, they have after one response, you got rewarded, after 10, after 20, after 30, and so on. But if you add all of these up together and divide by the number of different sets we have here, you get an average of 360. So that's our average ratio. In practice, you tend not to see them occurring in this specific sort of smallest to largest responses, though sometimes you will. Especially if you're trying to test how many times an organism will push a button to get a particular reward. Most of the time you're going to see it as a shuffled ordering, where sometimes they're low, sometimes they're high, but there's no particular arrangement there. Now, what does this look like on our graphs? Well, these look very different from what we just saw for our fixed ratio schedules with those nice consistent steps. In these cases, we can look at this. It's a little bit messier because this is real data. We still have ticks showing whenever reinforcement was given, but we see very, very narrow post-reinforcement pauses. So they either don't happen at all, or if they happen, they're very short. And so the existence of these post-reinforcement pauses is going to be influenced by the lowest ratio or the average ratio. So if we scroll back here, if you have to push the button 360 times in order to get reinforced, but on one trial, after only a single button press, you then got food again, then maybe you're not going to wait after you just got rewarded, because it could happen you could get rewarded as soon as the very next trial. So here we see two ticks very, very close together. That tells us that there were only a couple of button presses required to get that reward again. And you'll notice that the slope here is much steeper. So these produce higher rates of responding as compared to fixed ratio schedules because of that sort of degree of uncertainty where you're not quite sure when your next response or next reward is coming in. Variable ratio schedules are very common in natural environments. And this tends to encourage high rates of responding, so we also see it fairly often in research as well. A real life example of this would be gambling. If you're sitting at a slot machine, you never know which pulling down of that lever is going to win the jackpot. So that would be a variable ratio schedule, and you see high rates of responding because people are looking for that next payout. Now, when I first talked about the variable ratio schedule at the beginning here, I showed them arranged sort of in order of sort of shortest to longest delay between, or sorry, shortest to longest number of responses required, and then we showed it in shuffled ordering. There are actual names for that. The textbook doesn't talk about this, but it is kind of useful to know because you will see this in research. So if we have that shuffled arrangement, we can talk about it as a random ratio. So it's a variable ratio, random ratio, where the schedule would be controlled by some kind of random number generator. So maybe it's predetermined, whatever the scrambled order is going to be, and it's going to produce similar high rates of responding all throughout. This is what we see with our gambling, casino games, even video games has that sort of random number generator aspect of it. When we see them in order or increasing order, that's called a progressive ratio. So the requirements move from small to large. So at first you push the button once and then you get food, then twice, then 3 times, and so on and so forth. And as those ratios get larger, our post-reinforcement pauses also get larger because you are sort of picking up on the pattern of it takes more presses to get the reinforcement, so it goes sort of accordingly. And this is also how you would establish where's the break point? How many times will an organism do this particular behavior in order to get that reward? How much are they willing to do to get that reward? So this isn't as common to see, but it can be useful. So I just figured I'd point that out. Next, we're going to move on to intervals. And as I said, intervals refer to time periods. So it's going to be the same basic idea, but instead of number of button presses, now we're going to be looking at time that has to elapse. So for a fixed interval schedule, an FI schedule, the behavior is reinforced when that behavior occurs after a given period of time. So for example, a fixed interval of 4 minutes, we're saying that the first time you push that button after 4 minutes has elapsed is when you're going to get food. So you still have to press that button, but the number of times you press the button doesn't matter, it's when you press the button. And these fixed interval schedules absolutely produce these PRPs because as soon as you've pressed that button, you know that you have to wait a particular length of time before you're rewarded again. And so here we see a pretty neat pattern over on our diagram where we get these scallop shapes where you have to wait a certain amount of time. So right after a particular responding, so our little tick mark is here, we see a flattening out. And then after some time passes, the animal starts pressing the button, but they press it very slowly. It's sort of like they're checking, has enough time passed yet? No? Okay, I'll keep waiting. And so it ramps up where responding gets a lot more frequent as that reinforcement time gets closer until they actually get reinforcement and then they stop again. So we see this scallop shape here. This is very uncommon in the natural environment because it's a very set time period. So it's not necessarily useful. So this is kind of like waiting for your washing machine to finish. And so no matter how many times you go into the laundry room to check if it's done yet, you still have to wait the set time for your cycle before you can do anything with it. So if the cycle is 20 minutes, even if you go in at 18 minutes, it's not ready yet. So you don't get to do the behavior of swapping your clothes out until it has, until enough time has elapsed. And then for our variable interval schedule, this is, as you might predict, when the timing of the response is needed ends up varying each time, and that interval varies around a particular average. So a VI of 3 minutes is going to be where a response after 3 minutes plus or minus some kind of wiggle room is going to get you responding. And so as soon as we have this variable component introduced, there's a little bit of uncertainty, and our PRPs end up being very rare and very short if they do happen because of that variability. So we see kind of consistent responding here. Our tick marks happen either close together or far apart or somewhere in between because there's that variability there. And again, as with our variable ratio schedules, we tend to see fairly steady rates of responding, though this tends not to be as high rates of responding as variable ratio. And that's because the responding itself isn't necessarily controlling when you're getting the reward. It's the amount of time that has passed. So with variable ratio, the more you push the button, the more likely you are to get the reward, or the more likely to get that particular reinforcer. So here, where it's timing, there isn't as much motivation to sit and press the button indefinitely because time is a factor as well. And this is very, very common in natural environments. So this is like, you have to go get groceries, but it's going to rain today and you're not quite sure when. So maybe it's going to rain in an hour, maybe it's going to rain in an hour and a half, maybe it's going to rain in 15 minutes. You are not quite sure, but you know it's going to rain soon. And then if we look at sort of our idealized diagrams here and how they compare to one another, we see that our variable ones, whether it's ratio or interval, we tend to see fairly flat lines, minimal PRPs, with the variable ratio having higher rates of responding than the variable intervals. And then our fixed ratio and fixed intervals, we tend to see those PRPs, those sort of stepping offs where the responding reduces. And again, our fixed ratio, the slope is going to be a little bit steeper for the ratio versus the interval because button presses matter here and time matters here. And this, you might see it looking a little bit more scalloped. See the rounding here in the corners is kind of meant to be the scalloped effect where they slowly ramp up their behavior as that time period gets closer. So these are our ideals, and it might be a good idea to be able to tell the difference between all of these. So that's the end of the lecture. I just want to make a note that we are just a little bit over time on what would be a normal class period, but I didn't want to break this lecture up with sort of one class period length and then have like a 10-minute sort of tack on for the start of next class. So all I'm going to do is make sure that Thursday's lecture is a little bit shorter so that we're not going over our total lecture period for the week. So if you want to only watch what would have been covered in lecture today, if you want to watch the 80 minutes and then pause and you can watch the rest on Thursday, that's totally fine. I just wanted to keep it all together in one place, but I do want to acknowledge that this video is a little bit long and I will be accommodating for that because chapter 5 is actually quite a bit shorter because we've laid a lot of our groundwork and terminology in this lecture here. So just pointing that out.